2.3 in our book talks about continuity and the intermediate value theorem. So reviewing a little bit here, there are three conditions that must be satisfied for a function to be continuous at a point. The first one is the limit as x approaches c must exist. The second is that the function must be defined there. And the third one is that the limit has to equal the function at that point. Sometimes the third one is kind of considered like the shortcut version. So people will say, oh, if the limit is equal to the value of the function, then that kind of assumes that both of those must exist. The limit must exist and the function must actually exist in order for them to be equal. So it's kind of an abbreviated version of that. There's four ways a function can fail to be continuous at a point, and these are important. Two of those are called removable. So you can see the hole in the graph is a discontinuous function, and a hole that's defined to be something other than the hole also is discontinuous. A jump discontinuity you can see an example of, and an infinite discontinuity is anything that has a vertical asymptote. So continuity on an open interval is a thing that is, it makes great sense, I think. It just means that a function is continuous at every point on that. So an example might be something like the tangent function. If we look on the interval from negative pi over 2 to positive pi over 2, and if you remember what the tangent looks like there, it's going to have vertical asymptotes at x equals negative pi over 2 and also at x equals positive pi over 2. So since the curve does something like that, it's certainly continuous everywhere on the interior, and it's not continuous at those endpoints. So it's continuous on an open interval. An example of a function that's continuous on a closed interval might be something like the square root of 4 minus x squared. And I don't know if you recognize that or not, but it's going to be a semicircle. So it's going to look, let me change colors there. It's going to look something like that. So it's going to be continuous on the interval from negative 2 to 2, including the endpoints, the negative 2 and the positive 2. This is a little more interesting in terms of just the way it's defined, because you have an issue, since we say that the limit must exist, but we want to get around these endpoints here a little bit, because the limit technically doesn't exist there because the function is not defined on both sides, so it can't be, the limit can't exist because the function isn't defined on one side. But they just, we kind of just adjust our definition and say that the function is going to be continuous on all of the interior points, and then on the left side, so if we call that A and B in general, then if that limit as we approach A from the right is equal to f of A, that's going to work for us. And likewise on the other side, on the B side, the right side, if the limit as x approaches B from the right of f of x equals f of B, then we consider the function to be continuous at its endpoint as well. Let me go to a new panel. So here are some of the properties of continuity. If f and g are both continuous at x equals c, then so are c times f of x. So for example, we know that f of x equals sine x is continuous. You can imagine seeing that sine wave that's all nice and connected. So then so would if we took a function and said, say, 5 times sine of x, that would certainly be continuous as well. If we said that f was sine x and g was cosine x, then certainly if we define a new function to be sine x plus cosine x, that's going to be continuous everywhere as well. You can multiply those also. So a nice example might be if f was e to the x and g was equal to, say, cosine x, then if you defined a new function to be e to the x times cosine of x, that will be continuous everywhere as well. The only thing we have to worry about with f divided by g is that we don't want g of x to be equal to 0, because then we're trying to divide by 0, and that's not going to be continuous. But if we take something like, say, f of x is equal to sine x, and g of x is equal to, say, x squared plus 1, since x squared plus 1 will never be 0, then we can define a new function as, say, sine of x over x squared plus 1, and that will be continuous everywhere. For composition, it's kind of nice. F of g of x is continuous at x equals c as long as, well, we said in our condition up above that g was going to be continuous at c, so then we also need for f to be continuous at g of c. So, for example, if you said something like f is equal to e to the x and g is equal to, say, cosine of x, then if you define a new function to be e raised to the cosine of x power, that's going to be continuous as well. So nothing terribly earth-shattering there, although we will try to look at this idea of composition can be really tricky if we don't satisfy those conditions that both f and g are continuous everywhere. But we'll take a look at some of those at a later time. Let me talk about intermediate value theorem on another panel. So the intermediate value theorem, or it's also often abbreviated the IVT, says that if f is continuous on a closed interval ab and f of a is less than or equal to k is less than or equal to f of b, then there is a c in the interval ab such that f of c is equal to k. So this is one where the AP is really emphasizing understanding of the conditions, what are known as the conditions of major theorems. So you have to know what it must be true before you can make the conclusion. So there's three big conditions. F has to be continuous, we have to have a closed interval, and you have to have that this number k is in between f of a and f of b. And I've written here f of a is the smaller one, but it could go either way. And then our conclusion is that then there must be a c so that f of c is equal to k. So it's I think makes sense. It's a theorem about continuity. So if k is some number in between, say, f of a and f of b, then somewhere along here there has to be a number c, maybe more than one, where f of c is going to equal k. That is, we can't somehow come along here and skip over that value at k because of the continuity of f. So in practice, I mean, in theory, it makes, I think, pretty good sense, and I think it helps to remember when we get some other named theorems to help to remember that this is really about continuity. All right.